we are going to start today with a quiz. However, I did write another lovely little bell work here for you. I thought for sure we would have early release today. So just so you know, I removed this top. I think that this top section is so easy. Okay, so on the quiz, I don't even have that on there. Your quiz is going to start with I want moles from moles. And if I want moles from moles, which is already speaking the same language, all I do is I take what I'm given. I need an eraser. I take what I'm given and I say, all right, I have 2 lithiums that come off every lithium sulfide. So if I have 0.6 moles of lithium sulfide, I got 1.2 moles of lithium, and I multiply it by 1 for sulfur. Okay, so that's how you're going to do the front. And then the back is going to encompass kind of like the whole thing. Oh, let's see, I'm going to scroll down here. The back here says how many grams of each. Well, I'm in grams and I want grams, and one would think that this might speak the same language, but it does not, because the mass of an iron is 56 and the mass of a chlorine is only 35. So it's like comparing chicken eggs and ostrich eggs. Like, I can't compare them in grams. I can only compare them in moles. So first step on the back is probably the harder part. You're going to take everything you've been given and you want to put it into moles. So I'm going to take my mass, which is 4.83. I'm going to put it over the formula weight of my FeCl3. So 56 and 335 is going to give me 161 for a formula weight. I'm going to divide that in my calculator. And I tried to make a nice easy number for this first example here. 0.03 moles of FeCl3. Now, first step is get it into moles. Now, we're feeling like we were on the front side. If I want to know how many moles of iron come out of that, I'm going to multiply it by 1 for iron. I'm going to multiply it by 3 for my chlorine. Okay. Now, I know how many moles of each substance I have, but it asks for grams of each substance. So what I'm going to do is I'm going to do moles equal mass over the formula weight of 1 iron, and mass over the formula weight of 1 chlorine. I'm looking for mass, so in order to solve for x, I'm just going to multiply 0.03 by 56. When I multiply that together, I get 1.68 grams of iron. 0.09 times 35 gets me 3.15 grams of chlorine, and when you add them up, they should be pretty darn close, within a gram, okay, of what you started with. Okay, perfect. All right, so I would say don't even worry about that one that I just did. If I went too fast, I wanted you just to see it. I'd say let's see if we can't do this second one here. If you can get into there, we should be feeling good. I'm going to do some attention. On these quizzes, I'm going to give you this same slide like almost the whole entire time. And so I just remind you of a few things. I will not necessarily grade on figs, but if you want to get the exact same answers I'm getting, we should be getting into the idea of 2 significant figures after the decimal as you're rounding. That's like 10.23, 1.31, 0, 0, 25. 0, 5, 6. You need 2 numbers after the decimal when it's small. You're not giving me lots of numbers. I do still want final answers in moles or grams or whatever. You don't have to give it to me through the whole problem, but definitely on the final answers. I want to see enough work. Like, what formula weight did you use? I don't need to see how you got the formula weight. Just give me the formula weight. I'm usually pretty good at figuring out by now what mistakes were made. Moles equal mass over formula weight. You also have that on the back of your periodic table. When you are done, turn it in the A and B folder. And then what you're going to do is you are going to work on that lab from yesterday, trying to get to question 9. Okay? And what I want to do is I would like for you to go ahead, grab out your lab. And then I want to talk about kind of what happened yesterday, because yesterday was more of like a data collection day. So what you guys did was you did this reaction here that you wrote and balanced. You took your pure magnesium and you added oxygen to make magnesium oxide. Okay, so what we did here was we took this magnesium ribbon that was nice and shiny and we added oxygen to it. And you can think of it kind of like you rusted it quickly. You added oxygen like a nail rusts by adding oxygen to it as well. That oxygen came from the air and latched onto it. So I had a lot of questions yesterday because if you did your math correctly, for the next question, it says, how much magnesium oxide did you make? Well, this is the mass of my empty crucible, and this is the mass of my crucible with my MgO. So I just want to take out the mass of my crucible, so I subtract these, and what you should see is you get a mass. Now people are like, oh my God, the mass of my magnesium went up. And that is absolutely expected. You made a new thing that has oxygen attached to it. You made something heavier. It'd be like if I had this pen and it weighed 10 grams and then I put this cap on, it's now going to weigh more. Okay, you attached oxygen to your MgO. All right, so here we go. Let's go through some of these questions. So hopefully you guys got, for number 3, you took your initial ribbon and you divided it by 24 to get the moles. I would personally put 0.14 over 24 to get my moles, which would be 0.0058. How do we determine the crucible? Like I said, you probably did that already, or the MgO in the crucible, you probably did that already. It should have gone up. Nice. Now, how many moles of MgO is that? Well, I know moles equal mass over formula weight. The formula weight of 1 mg and 1 O is going to be 40. So I would take my final mass and divide it by 40 to get moles. So hopefully we're there. Awesome. Now we have a couple tricky questions. What is the mass of oxygen used in this reaction? And some people find a long way to kind of do this, and some people kind of see a shortcut. Okay, how much oxygen was used? Well, if my ribbon was 0.14 grams to begin with, and then I attach that oxygen, and now it is 0.23 grams, how do I know how much this bad boy is that I stuck on there? Okay, you would just simply take the difference. So I'm going to say that was my ribbon before the oxygen. This is my ribbon with the oxygen, that magnesium. So all you have to do is take a difference. Okay. There are different ways you can get to it. Yesterday I saw some creativity, but it's really just a straightforward. That's how much oxygen we added to your ribbon. All right, on the inside. So as the ribbon was burning, its mass was increasing. Where did that mass come from? We kind of just said that it's a synthesis reaction. You are adding oxygen from the air. Okay, it is latching on to that magnesium, making it more hefty. If you think back to the steel wool question at the beginning of the year where I took that steel wool and I burned it and somehow it became higher in mass, that's exactly what we're doing right now. We're oxidizing metals. If you got this far, and you might have, you should have done your moles of magnesium, which I think was the answer to number, I want to say 4, to the moles of MgO, which I think was the answer to number 6. If I'm not mistaken. And what you should have got was a 1-to-1 ratio. Okay? And the question here is why? Why is this a 1-to-1 ratio? Okay? Hopefully in the next 20 minutes I can get you doing full-blown stoichiometry. So what I want you to do, and I know it says notes, I just want you to get your notebook out where you have been keeping your notes. We're going to write one more sentence. I don't like to write a lot in stoich, but I want to write one more sentence here. Probably should have told you that from the beginning. I'm sorry. All right. We're going to write one more sentence in here. It's like a little running tally of tidbits that we're learning about stoichiometry. All right, all right. I don't even know that you got to write this whole title, but I do know that one of the last 2 things you should have information that says moles are how we count molecules. Got that written somewhere. You should have the word moles equal mass over formula weight. Got that written somewhere. And the last thing we wrote is that coefficients do not affect formula weight. We're going to talk about coefficients a little bit more today. I want to think, so these things are already in your notebook. We're starting right after that line. I want to just talk for a real quick second about that reaction that we did. If I could draw that reaction that we did, how would I draw that out? That would be 2 mg's react with 1O2, because remember, if we don't have a number there, we assume it's a little 1, okay? So 2 Mgs with 1O2 make 2 MgOs. Very interesting, okay? So let's pretend, so I need 2 of these. I'll write this on the inside of that. Okay, very good. Let's pretend I had, I don't know, 20 of these. How many of these would I need to react with 20 of these? I need 10 of these to react. And then how many of these can I make? I can make 20. Let's say I had, and you're not writing this down, we're just talking, we're just looking. Let's say I had 2 million magnesiums. How many million O2s would I need? 1 million. And then how many million MgO can I make? 2 million. Because we said our coefficient ratio here is a 1 to 1. For every 1 magnesium, I can make 1 magnesium oxide, okay? But I only need half of the oxygens to do it. Let's say that I had, I don't know, 400 billion magnesiums. How many O2s would I need to react with that? 200 billion. And how many billion magnesium oxides could I make? I could make 400 billion. Weird. Let's turn this into an interesting number that we can tell. What if I had 6.02 sextillion magnesiums? I would need 301 sextillion O2s, and that would give me 602 sextillion magnesium oxide. So what we're seeing here is a little bit of a pattern. If I had 1 mole of Mg, I would need a half a mole of oxygen to make 1 mole of MgO. I want you to write this real big in your notebook, and then I'm going to have you doing full-blown stoichiometry here in a second. While the coefficients do not affect formula weight, coefficients tell you the ratio of moles involved in your reactions. Coefficients tell you the ratio of moles involved in your reactions. Do I have 1 of these and 2 of those to 1 of those? Do I have 3 of those to 2 of these to 5 of those? Coefficients tell you a ratio of moles. Okay? So now I want you to put that packet back in front of you. I'm going to skip this bottom part so we can get right into the packet. Whenever you see an equation, and I'm going to lecture this on Tuesday, it should make you itch if it is not balanced. I see that this first equation is not balanced. Life can't begin until things are balanced, so I'm going to help you here. I see 1 sodium, I see 2 sodiums. I know I'm going to have to change that, so I'm not going to do that. 2 oxygens, I'm going to put a 2 here. How many sodiums is that going to end up getting me? That's going to get me 4. So let's pop 4 right out there. Okay, so my coefficient ratio, if I were to draw this, I would need 4 sodiums to react with, we're going to consider this a 1 O2, and then that can make me 2 sodium oxides. For every 4 of these, I need 1 of those, and I can make 2 of these. So let's say I had 40 billion O2s. For every 1 of those, I need 4 of these to react with it. So if I had 40 billion of these, how many billion of these do I need? 160. I need 4 times as many because my coefficient ratio is a 1 to 4. Let's say I have that 40 billion O2s. How many Na2Os can I make? This is a 1 to 2, a 1 to 2. If I have 40 billion of those, I can make 80 billion of those. Okay, awesome. I can start anywhere that we want. Let's say you have 0.8 moles of sodium. And I know for every 4 of these, I need 1 of those to react. So I'm going to go 4 to 1. I'm getting smaller, so I'm going to divide by 4. 0.8 divided by 4 is 0.2 moles of oxygen are required. It is a coefficient ratio. Now, you could go either way because you're going to get to the same number. I could say 4 to 2, 4 to 2. I need I will make half as many sodium oxides. So that's going to give me 0.4 moles of sodium oxide I can make. Or if you prefer to multiply, you can say that's a 1 to 2, 1 to 2. I'm going to double it. I need to make twice as many as I have. You still have the same thing. Let's try another one. If I have 3 moles of oxygen, I'm going to go to the product first. That's a 1 to 2, a 1 to 2. I will make twice as many sodium oxides. So I'm making 6 moles of sodium oxide here. And if I wanted to go backwards, okay, this is a 1 to 4, a 1 to 4, a 1 to 4. I'm going to need 4 times as many moles of oxygen, though, to get it started. I want to walk around, see who can get this last one for me. If you are feeling it, let me help you just a hot second. I'm going to balance that one for you. That's a 1, 2, 1, 2. So if you already finished that, go ahead on to the next one. You don't have to write trillion, billion, million. Just write the numbers for right now. We're saving some time here, okay? I want to see who can get this and who we can kind of get up on our pace here in a second. All right, you hold on. This is okay if we're kind of, if you're hanging off the train with me, that is okay. Let's get some numbers here. We got 0.084 and 0.021. If you're like rocking and rolling and you really want to get the fourth one, I'll balance it, or the third one, excuse me, I'll balance it for you. So it's a 132 on the back. If you can finish the ones that we are doing, go on to the back. But if you are not there yet, let's talk about this one together. So we got 2 people. You're either on the back working on that, or we're talking here. How am I going to do this one? All right, so I'm given 624 trillion H2s. This is a 2 to 1, 2 to 1, 2 to 1 ratio. So I need half as many carbon dioxides will be made. So that's 312. Then you might start to see if it is the same ratio. This is a 2 and that's a 2, and this is a 2 and that's a 2. So those numbers are always going to be the same. Okay, 0.18, 0.18. So, and then if I have how many carbon dioxides I have, I'm also going to need that many methanes. Okay, so let's do this next one here. Hopefully you're catching on. If I have 0.84 moles of water made, 2 to 1, I'm going to divide that in half here. 0.42, double it to get to my O2s, and then keep it all the same there. Okay, so if I have people going along, let's have you check if you need. Okay, the back was a little bit more challenging. I gave you some odd numbers to kind of keep some of my people that needed a little bit of a challenge there. If you don't get to the one on the back, I'm 110% okay with that. But if you did get to the back, the numbers we should be looking at are 10 and 20. You're looking at 0.1, 0.3, and then you're looking at 15 and 10. Now, we are going to put it all together in this last 5 minutes, and we're going to do full-blown stoichiometry. What I need you to do is look at this next one. These are real-life numbers, so I don't care if you finished anything up to here. Flip it over to the back. Let's do this. This is what your challenge lab will be on Monday. All right, if I have 5 moles, and this is one thing, 5 moles of barium chloride, and it wants to know how many moles of water am I going to produce? What is my coefficient ratio from here to here? If I don't have anything, I assume that's a 1 to 2. So if I have this much barium chloride, how many moles of water? I'm going to multiply this by 2. So I'm going to make 10 moles of water. Yes, it's a 1 to 2 ratio. Then The only other thing you have to add in to do full-blown stoichiometry is I want to know how many grams that is. And you guys know moles equal mass over formula weight. So I know that I have 10 moles of water. I know I want the mass of water over the formula weight of water. So I'm just going to do 10 times 18. Boom, that's how many grams of water you should get. All you got to know is how much you started with. Okay. There you go. It's beautiful. You're doing stoich now. Okay, I'm going to go ahead and balance this next one for you. That's a 2-2-1. It's a decomposition reaction. Stay with me here. I'm starting with 0.56 moles of water. I'm starting with 0.56 moles of water. The question says, how many moles of O2? So I draw a little question mark over here, and I say my coefficient ratio from where I am to where I'm going is a 2 to 1, a 2 to 1. Am I getting bigger or smaller? I'm going to divide that by 2, so 0.56 divided in half is going to be 0.28 moles of oxygen is going to be produced. But the question next is then how many grams am I going to get out of that? Well, here's one last tricky thing that people might get caught up on. I have moles of O2. I have what grams of O2 I need to multiply this by O2, which is 32. And if I do 0.28 times 32, you got 8.96 grams of oxygen. So we're just taking this idea of coefficients, tell us the ratio, and then using what we already know. Let's do another one. We only got 2 more. We can get them done. Let me take a moment here, and I'm going to balance both of these for you. So for number 3, 2, 3, 2, and for number 4, 4, 3, 2. Ready? Ooh, we're going to go backwards. It's going to be okay. Stay with me, or if you're going, you go ahead. The question here says, what is the mass of aluminum needed to complete this reaction? So I put a question mark. I'm trying to figure out the mass of that. I know I have 0.44 moles of AlCl3 I want to make. What is my coefficient ratio from here to here? That's a 2 to 2 or a 1 to 1. So how many moles of aluminum do I need? I need the exact same moles of aluminum, and moles equal mass over formula weight. Wait a second, I still have a minute. Oh. All right, why don't you write this number down here on the side and see if you can't get that answer sometime today. When you come in on Monday, I'm giving you a challenge lab where you're going to have to use this information. Okay? Good stuff, good stuff. Anybody? All right, if you are watching at home, we're going to finish this bad boy here, and we are going to say, okay. All right, so what is the mass of iron needed to make this reaction complete? And I want 0.11 moles of Fe2O3. I'm going from there to here, so that is a 2 to 4, and so you don't want to read it like a book. We read it from where we are to where we want to be. So I need twice as many iron moles as the iron oxide moles that I'm going to end up with. So if that is twice as much, I do 0.11 times 2 is going to give me 0.22 moles of iron is what I need. So I got that. And then the question, though, says, what is the mass of what I'm going to need? And so all I'm going to do here is interrupted by the announcements. Moles equal mass over the formula weight of 1 iron is going to be 56. So what I'm going to do is I'm going to multiply those two things together. That's going to tell me how many grams of iron I need in order to create 0.11 moles of Fe2O3. Okay? Perfect. Thank you guys very much.